When a population is described by a categorical variable rather than quantitative, all we can really do is to calculate the proportion of outcomes compatible with a given outcome, which we call a success. We learned that if we draw a representative sample from such population and the sample is composed by independent observations, we can describe the sampling distribution for proportions with a normal model, so long as we have at least 5 successes and 5 failures in the sample. This sampling distribution will be centered around the population proportion and will have a standard deviation given by the square root of the population proportion of successes times the population proportion of failures divided by the sample size. Let's now learn how to conduct hypothesis testing on a population described by the proportion of a categorical variable. We call this test the one-proportion z-test. Recollect the example of the truckload of apples. And just as we did when we build the confidence interval for proportion, let's examine the situation from the viewpoint of the inspector at the accepting station. The inspector's objective is to make sure that his employer purchases only high-quality apples for its grocery stores. If the inspector approached each truckload of apples by assuming the truckload not to be suitable for purchase and then placed the burden of proof on demonstrating that the truckload has golden standards instead, he probably would end up turning back most of the trucks coming to his accepting station. A more sensible approach would be to assume the truckload to be suitable for purchase and only turn it back if the inspector gathers enough evidence that the truckload really contains enough bad apples not to meet the company's standards. As we saw in the previous lessons, the criteria set by the company is to reject a truckload of apples if it contains at least 6% of bad apples. Therefore, the inspector will give the benefit of doubt to the truckload meeting standards and set the null hypothesis for all those outcomes in which the population proportion of bad apples does not exceed 6%. Conversely, the alternative hypothesis will contain all the outcomes in which a truckload would be turned back, such as the population proportion of bad apples being greater than 6%. Also, let's choose a significant level of 0.1 this time. This is not an unreasonable significance level because if a lower one had been chosen, such as 0.05, then the inspector may end up accepting too many truckloads with excessive amounts of bad apples. And that obviously would eventually hurt the business too. If the inspector collects a random sample of 80 apples, then we can assume the sample to meet all necessary inferential conditions for the sampling distribution of proportion to be normal and center around 6% because we have assumed the null hypothesis to be true. Using the formula seen before, we can estimate the standard deviation of the sampling distribution for proportions to be about 0.0266. Remember, because we assumed the null hypothesis to be true, then we also assume to know the population proportion. That's why we can calculate the standard deviation rather than the standard error. If we suppose to tally 8 bad apples out of the 80 in the sample, then the sample proportion is equal to 0.1 or 10%. We can now locate the sample proportion on the sampling distribution by calculating the test statistic, which is the z-score. Plugging in the values, we obtain a z-score of 1.5. Because the alternative hypothesis has inequality greater than or equal to, this qualifies as a right-tail test, as the p-value will only be in the area to the right of the sample proportion. Using the Excel formula norms dist, we can calculate the p-value to be about 0.067, which is less than a significance level of 0.1. Therefore, we can reject the null hypothesis, and the inspector has enough evidence to turn back the truckload of apples, as it is likely to violate company standards. The z-critical approach works just as seen in the previous 2 videos. First, we identify a right tail of 10%, which is our significance level, and therefore a complement of 90% for the left tail. Second, we calculate the z-critical corresponding to such percentile using the Excel formula norms_inv, which is equal to 1.282. Third, Because the test statistic of the sample proportion is equal to 1.5, as seen before, it means that it is greater than the z-critical. Thus, we reject the null hypothesis just as we did for the p-value approach. In the previous videos, we considered the sample requirements for the one-sample z-test in which the population standard deviation sigma was known, and the one-sample t-test in which sigma was unknown. Now, we will consider sample requirements for the one-proportion z-test in which the variable of interest is categorical rather than quantitative. As you may recollect from the example we just considered about the test on the truckload of apples, we can compute the test statistics z as follows. At the numerator, we have the difference between the sample proportion and the hypothesized population proportion, whereas at the denominator, we have the standard deviation of the sampling distribution of the sample proportion. You may recollect that we can write the standard deviation of the sampling distribution as the square root of a ratio having the product of the sample proportion of successes and of failures at the numerator and the sample size at the denominator. If you plug the expression for the standard deviation of the sampling distribution into the formula for the test statistic, we obtain the following expression for the test statistic. Using the z-critical approach, we learned that for a right-tail test, we can reject the null hypothesis when the test statistic is greater than or equal to the critical score at a given significance level. And note that because here we consider a right-tail test and we are not concerned with the left-hand side of the sampling distribution, the critical score is positive and there is no reason to consider the modules as we did for a two-tail test. If we plug in the formula above for the test statistic, we obtain the following inequality. Let us replace the variable sample proportion with a target sample proportion by adding an asterisk to its symbol. If we move the denominator of the left-hand side to the numerator of the right-hand side of this inequality, and we bring the hypothesized population proportion to the right-hand side of the inequality, we can estimate a lower limit to the possible values of the sample proportion for which we would reject the null hypothesis. And if we now multiply both sides of the inequality by the sample size, we can make a few simplifications. To the left of the inequality, the product of the sample size times the target sample proportion is just the target sample for the count of successes. Or in other words, x asterisk represents all possible counts of successes for which we would reject the null hypothesis. To the right of the inequality, the product of the sample size and the hypothesized sample proportion represents the expected count of successes, and we can bring the sample size inside of the square root, thereby simplifying its form. Let us consider an application of this approach to the truckload of apples example. As you may recollect, in the example we just saw, the hypothesized population proportion of bad apples in the truck was set at 0.06, which is the threshold set by the inspector at the accepting station. And the sample collected from the truck consisted of 80 randomly selected apples. In the previous example, we also set the significance level alpha to 0.05. Because this is a right-tail test in which we are testing for whether the population proportion is greater than the hypothesized 0.06, and because we have at least 5 expected successes and failures, then we can assume the corresponding sampling distribution to be normal with a critical score equal to 1.645. If we now plug the data into the inequality shown in the bottom left of the screen, we obtain the following numerical expression, which, when simplified, leads to an estimate for the lowest count of bad apples in the truckload needed to reject the null hypothesis and conclude the proportion of bad apples in a truck exceeds company standards. Note that we can't really have fractions of apples, so we can relax the number to the right-hand side of the inequality by rounding it up to an integer of 9 bad apples. If you recollect the result of the one-proportion z-test considered earlier in this video, we suppose that there were 8 bad apples in the sample, leading to a low p-value, but just not low enough to reject the null hypothesis. If we have had one more bad apple in the sample, in this case 9 bad apples out of 80, we would have had a higher sample proportion, which would have led to a lower p-value, which in turn would have given us enough evidence to reject the null hypothesis. let us now go back to the inequality formula for the rejection of the null hypothesis. You should remember that the fact we failed to conclude the population proportion is greater than 0.6 does not necessarily imply that the population proportion of bad apples in the truck meets company standards. It simply means that the test is not powerful enough to detect that it doesn't. Well, we know that we can make a sampling distribution narrower and therefore the test more powerful by increasing the sample size. Therefore, let us now focus on the sample size n at the denominator and define as target sample size n asterisk the range of sample sizes at which we can reject the null hypothesis. If we now solve for the target sample size instead, we obtain the following inequality. Again, let us consider as an application the example of a truckload of apples. The hypothesized population proportion of bad apples in the truck is still the same, at 0.06. And recollect how in the 1 proportion z-test example considered earlier, we had 8 bad apples out of 80 with a corresponding sample proportion of 0.10. And let us also keep the significance level alpha at 0.05 with an associated critical score of 1.645 for a right-tailed test. If we now plug the numbers into the inequality shown in the bottom left of the screen, we obtain that we need a minimum sample size requirement of 96 apples in order to have a reasonable shot at rejecting the null hypothesis. As you can tell, this estimated sample size is not much larger than the original one of 80 apples. But after all, we know that the p-value was already quite low before, and in the end, we also know that a truckload of apples, unbeknownst to the inspector, contain 8% of bad apples. So it only makes sense that a more powerful test, obtained by collecting a slightly larger sample size, should be sufficient to detect the true population proportion of bad apples in the truck.